This is a really good lesson because it reinforces two things. It reinforces a lesson we just did on the derivatives of natural logs, and it also reinforces integration by substitution. So this is going to be some really good practice for us if we focus and try to learn things from here. So what we want to recognize is that we learned in our last lesson that the derivative of the natural log is 1 over x, or 1 over u du if there's a function inside there. So obviously the integral would just be the inverse of that, going backwards. So the integral of 1 over x is the natural log of x. We have the additional absolute value of x on there, and then plus the constant. Don't forget the plus c. That was something that some of you were doing in the tests. And it was weird because sometimes you would put plus c and sometimes you would leave it off. So that's a little bit strange. But so we do want to make sure that we understand that when we think about like x to the negative 1, we're not adding 1 to the exponent and dividing by the new exponent. That is not that case. So any other negative exponent, x to the negative 2, 1 over x cubed, those we would just add 1 to the exponent and divide by the new exponent. But this one case we would not. This one case we want to recognize that 1 over u is the natural log of u. So when we look here, this is just going to be, we want this to be 1 over u. So we want to do a little u substitution there with 6x plus 1. So du is 6 dx, and we don't have an extra 6. This 6 is part of the u, so we need to divide both sides by 6. So if we make that substitution, we're going to have dx is 1/6 du, and then this is 1 over u. So that should be kind of really nice review of integration using substitution. 4.5, I believe, section 4.5. So when we integrate that, that's going to be the natural log of u plus c, and we probably didn't need that step. We probably could have substituted that back in at that point. So that would be our final answer there. All right. So here we have this 1 over some stuff, so we want to think, well, maybe that could be the natural log. We do have other exponents here, but there's too much stuff to just rewrite that with a negative exponent and think we could handle that. So what we may want to do here is, this looks a little more complicated than that. We have two terms here. So maybe u will be x to the 1/3 power plus 1. So du is going to be 1/3 x to the negative 2/3 power dx, subtracting 1 off the exponent there. Now, actually, x to the negative 2/3, that works out perfectly. It's right there. And we will do a double underline there for this and this. So we don't have this 3 taken care of, though, so we do need to multiply both sides by 3. So we're going to have 3 du equals dx over x to the 2/3. So that, pretty nice substitution there. So that's going to be this x to the 1 over x to the 2/3 dx is equal to 3 du. And then this is going to be 1 over u. Okay, so the double underline gets replaced with this, and then that's our 1 over u right there. So that's pretty nice, I think, hopefully. So now let's go ahead and skip the step with the u and just let's replace the u with the x to the 1/3, so we don't have to write it down basically twice. There we go. Okay, so this is a great practice for substitution and just working on some things, reinforcing skills that we're supposed to have from first semester. Okay, so find the area. So first of all, area is synonymous with integral, hopefully, just like slope, tangent, derivative, slope. So integral area. So we want to find the integral of that. So we're going from 1 to e here. 1 to e. This just cutting off the bottom, so that is going to be here. Now, this would be a good place to pause and think about what that should mean to you, and it should mean something right here. Okay, so I've talked about that plenty of times. So that is a single term in the denominator. Usually means we want to split that up. Reverse common denominator. We don't want to take them apart. Okay, so think about what we're going to get there. That's going to be 1 over e. This side will be 1 over x, and then next to it we're going to have x to the negative 2 power. Okay, so great review here. Well, this is not review, this is today's lesson, and then this is a review from chapter 4. So if we focus on this part first, that's going to be the natural log of x. And then if we add 1 to the exponent, that's going to be x to the negative 1, and then divide by the new exponent, so divide by negative 1, so that's going to be here, and that's from 1 to e. Okay, so if we plug e in here, we're going to have the natural log of the absolute value of e, but the absolute value of e is just e, so I can put that. And then minus 1 over e, and then minus, I need to be careful here, I need to put parentheses because I'm plugging this back into both of these. So that's going to be the natural log of 1 minus 1. Okay. So the natural log of e to what power equals e to the first power equals e. So that equals 1. And then this is 1 over e still. And then this is minus, so e to what power equals 1? E to the 0 power equals 1. So we want to memorize that that is equal to 0. That would be helpful. And then we have opposite of negative 1 would be positive 1. So this is going to be 2 minus 1 over e. Okay, we really want to learn what we're doing in these notes. That's why we're taking the notes. They're the most important thing. Practice and learn from your notes. Slide here. Whoa! I don't know if that cuts down the shadow a little bit there or not, but we'll see how that goes. So, when you first look at this, you might say, oh man, that looks a little bit scary, but hopefully you see a connection between the numerator and the denominator. So, like, how do you know what to do? Well, when there's a lot of stuff, you're probably going to have to use u substitution. And when you see that that is 1 power less than this, when you see that that's the derivative of this and this is the derivative of this, that's a pretty good sign. So u is going to be x to the 5th minus 3u. So if we take the derivative of that, it's going to be 5x to the 4th minus 3 dx. So there you go. And that is really nice because it's right there. So that whole thing is going to go. So that's super nice. Bam. And we're pretty much done here. And again, we're going to skip the step with the u and just plug in the substitution back. So there we have that one. That was probably the nicest one of the three, maybe. Okay. Now, usually they don't throw this a lot of algebra on the AP test, but I have that it was on the AP exam here, so it must have shown up recently that I wasn't used to. So the problem here is that when there are two terms down here, so we can't separate it. If we take the derivative of this, we get 1. So we have this extra stuff. That's a problem. We want to try long division. This technically would be a way of rewriting, so I could put a heart there because that's what I put to indicate that we are rewriting things. So if we take x minus 1 divided by x plus 1, we can see what we get there. So we're going to multiply that by 1. So that's going to be x plus 1. And then we're going to subtract that, just like we do with the normal long division with numbers. So when we x minus x, when we do the digits, we subtract. So that's gone, and then we have negative 1 minus 1, so that's going to be negative 2. So that's a common mistake, is to make sure that you distribute that negative. That's why I always put this in parentheses. When I taught pre-calculus, put that in parentheses and distribute that negative. So now we have a remainder, and so we put the remainder over the divisor. So we have that. And so this integral now becomes, and most integrals can't be integrated, but in AB especially, we focus on ones that can be integrated with these little tricks. And in Calculus BC, we learn more tricks on how to integrate some things from pre-calc and then some new things. So if we integrate this, we add 1 to the exponent and divide by the new exponent, so that would just be 1, and that's it for that. Now here, you could do a u substitution on that, but hopefully it's not that big of a deal. You have the 2, and it's 1 over u, but du is just dx, so hopefully that's not a big deal to anybody. If it is, you can write out the substitution so that you can see it better. But really, I would think we could just do it there. Okay. Now, actually, do we want to do that? That would be. There's another way around that, where we actually could just use u substitution with a technique that we did back in chapter 4, but it's a lot more work. Maybe I'll show it to you real quick, and you can kind of decide for yourself. So if you let u be that x plus 1, then du is going to be dx. But if you go back and you say, okay, well, hold on here, let's see, what does x equal? If you remember, if we solve this for x, then we get u minus 1 equals x. So we can substitute in there. So if we substitute u minus 1 in for x, u minus 1 minus 1 over, and then that was u, and then du. So we're going to have u minus 2 over u du. So now you can decide, well, is this more work than that? Like, which way would I rather do this problem? So here we have a single term, and we can split that up. So that's going to be 1 minus 2 over u. Okay. And now we can integrate that, and that's going to kind of go like this, and then we would need to substitute that back in, and we would get that. So I don't know that we need to finish that necessarily. Hopefully you can try that if you want to. Alright, so over here we'll do the same thing. So we have x cubed plus 2x squared minus 4, and so one difference is, if you notice this problem here, the degree of the numerator was 1 less than the degree of the denominator, so that worked out pretty well here. If the degree of the if the degrees are equal, or if the degree of the numerator is larger, then that's a good indication that you're using long division. So little hints to help you decide which technique you should be using. So here we could put x there. That's going to be x cubed. And what I made a little mistake there, sort of, and I should have put a placeholder in, if you remember from your pre-calc and algebra 2 days. There should be a placeholder there for the x spot. So this is minus 2x, that would go under here. Now again, I'm using the parentheses there and subtracting to emphasize, distribute that. So that's going to cancel. This comes straight down. That's not affected by the negative, so that's 2x squared. And then this is subtracting a negative 2x, so that's going to be plus 2x. And then bring the 4 down, like so. And then now we want to try to eliminate this, so we're going to multiply that by 2. So plus 2, so that's going to be 2x squared minus 4. And again, parentheses distribute this subtraction, so that cancels out. 2x comes down, that cancels out. Now we're left with 2x, so that's our remainder, and the remainder goes over the divisor. Alright, now we're going to integrate that. So if we integrate that, maybe I can put that up there, save us some writing instead of having to write that down again down here. So if we integrate that, that would be add 1 to the exponent, so that would be x squared divided by the new exponent would be 1/2. And then here, add 1, and that would be make it a 1, and then divide by 1, so that's fine. Now, the next thing we have is this. So that's where we might want to use a u substitution to integrate that. And we can tell because the degree of the numerator is 1 less than the degree of the denominator. So if u is x squared minus 2, du will be 2x dx. And we do have a 2x dx there. That's nice. That works out perfectly. So that would be, that would just be 1 over u du. This whole thing fits into that super nice form there. So now if we integrate that, we get the natural log of x squared minus 2 plus c. Bringing that part up from here. Alright. So, moving right along, we see some things here. And what we want to do here is multiply both sides by dx, and then integrate both sides. So those dx's cancel. Oops, I don't want to cancel that one out. I wanted to put it over there. So don't cross that one. I crossed the wrong one off. Okay, so dx right there. So that's a pretty nice substitution there, x squared plus 9. I hope you're pausing these and not just copying me. The point is not just to get these done, it's to learn how to do it. And if you're really practicing this, it should get easier through the notes as you take the notes. 2x dx. Right, we could get some 9th graders to copy these notes down. That doesn't mean that they know how to do it or that they understand any of it. When you're solving a differential equation, you want to remember that you need to separate and integrate, and then a lot of times we need to evaluate, but there's no initial condition here, so we're just separating and integrating. Alright, so now the 2x dx is right there, so that's pretty nice. So that is going to just be, the integral of dy is just y, and here we would have 1 over u. So that's going to be the natural log of u plus c. And if you want to check, you could take the derivative of that to make sure that it equals that. And so sometimes the book will say take the derivative to make sure. So this is a nice little check on the lesson that we just did. Remember, it's 1 over u times du, which would just be 2x in that case, and then the derivative of a constant is 0. So that works. Check to check your work. Okay, so let's do another one over here. So this one looks a little bit tricky over here. So again, we're going to multiply both sides by dx, and then we're going to integrate. So this looks a little bit messy. Probably need to do a u substitution. If you're not sure what to do, it's probably u substitution. So the question is, what do you want to let u be? And your first thought might be, well, let's let u just be x squared, but then you're going to have this log here, which is going to cause some problems. So let's try the log of x squared first. So the derivative of that is going to be 1 over u times du, which would be 2x. Okay, dx. So that reduces to 2 over x, and we do have an x here, so we have dx over x, which is what we would have from here, but we don't have that 2. We have the 2 down here. That's not helpful. So we need to divide both sides by 2. So let's go with that. All right. So that's a nice substitution on that, and we have that 1/2 there. So if we do that now, we're going to have y, and then we have 3 halves here. I don't know if I want to confuse anybody. Maybe I better write. So 3 halves from here, and then from here we're going to get another 1/2. Okay, and then this, so that's out of the way, that's out of the way. So this is 1 over u, so the derivative of 1 over u, I don't know if I should have left that out or not. So that would be 3 halves times 1/2, the integral of 1 over u du. Using the substitution and writing it out, I was going to kind of skip that step, but that's what that would become. And then that's going to be the natural log of u, which is the natural log of x squared. So that's a little bit awkward, but let's wrap that up. So 3/4. So I probably could have combined these. That's a little bit. So it's a log inside of a log, which looks weird, but it is something that can be done. So, all right. Moving right along. Integrals of trig functions, page 329. Trig functions, we either have them memorized, or we use u substitution, or we use an identity. Those are the 3 techniques, the main techniques that we want to try there. So let's think about what we could do here. So the integral of tangent. Tangent is not the derivative of anything. So that's a little bit tricky. So what we could do is, that's not something that we have memorized. Tangent is not the derivative of anything. So that's not going to work. So let's try u substitution and an identity, actually. So tangent is sine over cosine. Okay. So if we let u be cosine, then du would be negative sine, right? But there's no negative, so then the negative is going to go with the du. We're going to divide both sides by -1. So that's right there. So now we have negative 1 over u du, because sine x dx can be replaced with negative du. And then that's, wait a second, I think I have an extra negative on there. Let's get rid of that. I already factored it out. I shouldn't have had 2 negatives there. That's where the negative comes in. Alright, so now if we integrate that, that would be the natural log. The integral of 1 over u is the natural log of u, which was the cosine of x plus c. Now, the directions say to express that 2 different ways. So if you think about it, using the properties of logarithms, we could take that in as a negative exponent. So we would have cosine x to the -1. And that would be the reciprocal. That would be 1 over cosine. And so hopefully some of you know that 1 over cosine is secant. So that would be another way that we could express that. Okay. Now, if you look on page 329, you'll see the integral for secant. They just write it out, so it is something you could memorize. So we still would have, we still could do a u substitution on the inside there. So du would be 1/2 dx. So 2 du equals dx. So if we substitute that, that would be secant u du, like that. Now, if you have that memorized, that's going to be 2 times the natural log, and the integral of secant is going to be secant u plus tangent, secant plus tangent. Now, that might not be that hard to memorize, because if you think about the derivative of secant, the derivative of secant is secant times tangent. So that's kind of, if you combine those two things, that might make it easier for you to memorize. Okay, so that would be memorized from page 329 of your textbook. Would be one way you could handle that. Okay, so we keep going here. So let's think about this. As soon as you see average value, you should be doing 1 over b minus a. So that's 1 over that, and then from there to there. So that is automatic. Like, anybody can memorize that. Well, not anybody, but most people should be able to memorize that. So, and sometimes on the AP exam they'll give a point for that, for having the coefficient and the limits of integration. So that's a nice one for us. Okay. Now, what should come to mind when you see this? So I'm going to do a little thought bubble here. And that's one of those, it's got a trig function squared, so we should be thinking of a Pythagorean identity. So I'm thinking sine squared plus cosine squared equals 1. And cotangent, tangent is sine over cosine, so cotangent is cosine over sine. So I want cosine over sine. So I'm going to divide this whole thing by sine squared. So that's going to be 1, and then this is going to be cotangent squared, and then 1 over sine squared is cosecant squared. So I don't have those memorized, I just have that one memorized. And then there are kind of 9 Pythagorean identities, technically, but the other 8 I can all find from that one. Okay, so that is the square root of cosecant. So we have the square root, and when you take the square root of something squared, you get the absolute value. So it's going to be the absolute value of cosecant x dx, if we switch that up. Okay? So if you think about that, if secant is this, then cosecant will be the negative of that. Okay, so first of all, this is a complex fraction, so I'm going to multiply by the common denominator. So that's going to be 4 over, this is 2 pi minus pi, so that's just going to be pi. Now, the derivative, the integrals, the derivatives of the cofunctions are negative, so that's going to make this negative. And then, if we compare it to that one, that's going to be the natural log. And then secant was secant plus tangent, so cosecant is going to be cosecant plus cotangent. And if you're wondering about a negative, that's out here. And then that was going from pi over 4 to pi over 2. Okay. So, that's going to give us negative 4 over pi, and then we're going to have the natural log of the cosecant of pi over 2. Cosecant is Cosecant is 1 over sine. Sine of pi over 2 is 1. So that's going to be 1. And then cotangent of pi over 2. Cotangent is cosine over sine. So that would be cosine of pi over 2. Cosine of 90 is 0 over 1. So this is 1 and this is 0 over 1. So that's going to be 1 plus 0. Plugging in pi over 2. And then you're going to get minus the natural log plugging in pi over 4. So when you plug in pi over 4, you're going to get 1 over sine, so that's root 2 over 2, and then plus cotangent of pi over 4 is just going to be 1, because it's cosine 45 over sine 45, and they're both root 2 over 2, so that's going to be 1. Okay, so this is the natural log of 1, which is going to be 0. So that leaves us with negative 4 over pi times the natural log of, if we multiply this by 2 over 2, that's 2 over root 2, which is 2 root 2 over 2, which is just root 2. So it's 1, I'm going to switch those around, 1 plus root 2. Alright, so that is that, and we are down to our AP review question here. Now, we've already done A and B earlier in the notebook, so normally I would have us do those again to practice, and that would be a really good idea for you if you feel like it right now, which I doubt you do after 32 minutes. But these are earlier in the notebook if you want to go back and look at those two. So let's look at part C here. That would be the new part of this. So for C, for runner A, if we want to know the total distance, we would take the integral from 0 to 10 of the absolute value, because it says total distance. So total distance is the absolute value of the velocity of runner A from 0 to 10. Okay? Well, that velocity was given in a graph, and so when we integrate a graph, and again, this would be good to pause, but when you integrate a graph, that's going to be area. So we just want to find the area of that thing, and you want to make sure you check these numbers, and it is 0 to 10, so that's fine. So that's going to be a trapezoid, so it's 1/2 the top base, which is 7, plus 10 times the height, which is also 10. So, and then that's going to be meters. Now don't get confused. Well, that's an area. The area is just giving us the integral. The question is, how far did the person run? And that's another thing. We integrate a rate, the velocity. When you integrate a rate, you get an amount. Okay? So the amount of distance is meters. Okay? So that was quick. And then for runner B, we would do the same thing. So we're going to integrate from 0 to 10 the absolute velocity of runner B, and that you're going to do on the calculator because they gave you an equation. So if you need to find absolute value, that is under catalog, and it should show up. That should be the first thing that shows up. But if it's not, you can hit the letter A and it should take you to the A's, and then you should see that first. So when you type that in your calculator, you should get this. Make sure you go to 3 decimal places. I can't believe how some students don't do that. So let's wrap this up. Like I said, it would be great practice if you would do A and B there, but that's up to you. Have a good day. It's about that time.